Hi, everybody. Hope everybody's doing well as we continue our remote learning here. Let's see. So we've got today and then at most two more of these coming out in the next 2 weeks. It would be at most two. And then we'll be looking at the AP test coming up pretty quick after that. And then the school year is going to be over. And we can all maybe relax a little bit more at home without school to do, both on my end and your end, right? But stay positive. It's important. So keep pushing on, and here we go. The next thing we're talking about today, what we're going to talk about is torque. And torque, just like last week, we're continuing to talk about things moving in a circle, and there's a lot of parallel between things going in a circle and things that aren't going in a circle. And what torque matches up with is forces. Torque is a lot like forces, and the two go together in more than one way, actually. But anyway, torque, we're basically going to be talking about forces again, but this time in a circle. Okay, so how is torque like forces? So let's remember that when a force is applied to an object, it causes that object to accelerate. And that just means speed up or slow down. So for example, when you're pushing a shopping cart through the grocery store, when you first grab that cart, right, it's not moving, and you push on it, which means it accelerates, right? So you push, a force is just pushing on something or pulling on something, making it speed up or slow down. Another example is friction, right? If you push something across the floor and you let go, it doesn't keep going forever. What stops it? Friction. If there wasn't friction, it would keep going forever, though, right? If there are no forces on an object, then it has constant velocity. So, like your phone, when you set it on the kitchen counter, gravity's pulling it down, the counter's holding it up, and those forces cancel out. And so the phone has a constant velocity, and that velocity happens to be zero. But it doesn't have to be zero. It just means that the velocity is constant. So, like an asteroid flying through space that is all by itself. It's not around a sun, or it's not around a planet. It's way out there by itself. And so that means there's no friction out there because there's no air. And so that means it will just keep going forever, right? There's nothing pushing on it, nothing pulling on it, but it'll just keep going because that's Newton's first law. Something that is in motion will stay in motion. And something at rest will stay at rest. There may be, but there may be several forces. If they all cancel each other, then once again the object will have constant velocity. But if they don't cancel, then the object will accelerate. So speed up or slow down. And so torque kind of follows these same principles. Okay, torque works the same way, but just in a circle. And the example that I'm going to use right here is a door, because you all know what a door is. You all have used a door in your life. Push on a door and it opens and closes, and it does move in a circle, right? Where's the center of the circle? Right at the hinges, right where the door is attached to the wall. That's the center of your circle. And the door, when you push on it, will swing around that circle, either open or to close, right? So and that's when you push on it, because it moves on a circle, you're applying a force, but the door experiences a torque because it's moving in a circle. So that force manifests itself as a torque to the door. So you would ask yourself, well, I'm using a force, and if the door could talk and you ask the door, Mr. Door, what do you feel? Are you feeling a torque or are you feeling a force? He would say that he's feeling a force because he's moving in a circle. If no one applies torque on the door, it stays still. Kind of like this second bullet up here. If there's no forces, then it has constant velocity. Same thing. If no torque is applied to the door, it stays still, or will continue to rotate at constant velocity if it was already rotating. There may be several torques on the door. For example, two siblings having an argument may be on opposite sides. One sibling might be trying to push the door closed, and one sibling is trying to push the door open. If they cancel each other, then the door will have constant rotational velocity, just like with forces. If they don't cancel, then the door will accelerate, right? So if somebody's stronger than the other one, they win, and either they get the door open or they get the door closed. All right, so that's how these two line up. If you notice, some of these bullets line up almost word for word, except with torque instead of force. Like the first bullet here goes with the second bullet down here. If you exert a force, then that object will accelerate. If you exert a torque, then you cause it to accelerate, just in a circular direction. It'll rotate. Second bullet, if there's no forces on something, then it has constant velocity. Same thing with torque. If there's no torque, then it stays still, or will have constant velocity. The last one up top, there may be several forces. If they cancel, then it's constant velocity. Look at the fourth bullet down here. If there's several torques, then they cancel. Fifth bullet, if they cancel, then constant velocity. Back up here, and the third bullet, if they don't cancel, then the object will accelerate. Same thing with torques, right down here at the bottom. If they don't cancel, it will accelerate. Okay, so let's move on to how they're connected by math. So you push on the door, and you are exerting a force, and that force is related to the torque just by the radius. Just so the distance from you to the door. So I'm going to put down these definitions right here. T, this is tau. It's a Greek letter. It's a little t, and its name is tau, and that's what we use for torque. The units for torque are Newton meters, and we abbreviate that NM, Newton meters. F with this little symbol here means perpendicular. That's from geometry. And that's F is force, just like it always was. We still measure that in newtons. N. Just to go through the details of force, the force here in this equation is the amount of force that is perpendicular. So remember, that's a 90-degree angle, right? Perpendicular means 90 degrees. So this F is the amount of force that is perpendicular to what we call the lever arm, which all that is just the lever arm is just whatever solid object is being rotated, like the door. In this case, the lever arm is the door. Okay, so we're looking at how much force is perpendicular to the door. Okay, so to try and see why the force matters for torque, right? What I want you to do is actually go up to your door. What I have here is a little illustration of a door. The big black dot is the hinges where the door is connected to the wall, and the black line there is the actual door. I want you to go try and open or close a door two different ways. First, like this blue arrow, just push straight at the door, make a nice 90-degree angle, your hand flat up against the door, and try and push it open. It's usually pretty easy, right? And then try it like this red arrow, where you're not pushing straight against the door, you're kind of pushing awkwardly, like at an angle. Your hand is not going to be flat against the door. You're going to have one, maybe two fingers on it, and try pushing on the door that way. And tell me, which one is easier to open it? If you go straight on, or if you go at this oddball angle right here? It should be that straight on is easier to open the door. You can make the door rotate easier. You can put a torque on the door a lot easier if your force is straight onto the door. All right, R is the radial distance. So all distances are measured in meters. So that's just how far the force is from the point of rotating. So what I want you to do is go back to your door again and try closing it two different ways. Try closing it at the end. Put your hand flat against the door both times. The first time you're going to put your hand at the end and open or close your door that way. Then the next time you open or close your door, I want you to put it where this red arrow is, just like a couple inches from the hinge. And tell me which is more difficult, if you do it at the end or if you do it on the close to the inside. And it should be that it's really difficult to do it where this red arrow is. It's kind of hard to push your door open from that spot. And that's because you need more force to put a torque on the door. You need more. Your R is small, so you need a bigger force to put the same torque on the door. Okay. Another point about this radial distance, you don't measure it necessarily from end to end. You always measure it from where it's rotating. Okay, so in this one here at the bottom, I've got my black dot in the middle. And so this one's going to rotate around the middle like that, kind of spin right around the center. And so if I was measuring this distance, I would measure just from the red arrow to the black dot. I would not measure all the way to the end. I would only measure from the red arrow to the black dot. But like our door case here, It's not spinning around the middle like that. It's on one side, it's stuck to the wall, and so it would spin more like this, around, like kind of like the hand on a clock, right? Makes that kind of spin. So in this case, I would measure from end to end because that's where my rotation point is. That's where my black dot is. It's at the end. That's the only reason I would measure to the end, is because that's where the center of rotation is. Okay. So what do we do when the force isn't perpendicular to the object or the lever arm? Okay, and that's exactly what we got a picture of. Here's our door again. There's the hinge. I've got a force, and I'm pushing on the door at this odd angle instead of pushing right at the door. So how would we mathematically do that? So we're just going to use some geometry. First thing we're going to do is we're going to measure the angle between the force, our red arrow, and the lever arm. And that theta symbol, it's just a Greek letter, theta, that mathematicians and physicists always use for angles in a picture, just to label it. Okay, and then what we're going to do is we're going to draw a dashed line from the force arrow to the door, and this dashed line is going to get to the door at a 90-degree angle, because remember, what matters is the amount of force that is perpendicular to the door. And so that's exactly what the dashed line represents. The red arrow is the full force. The blue dashed line is just how much of F is perpendicular to the door. Not all of it is perpendicular to the door, but some of it is. That's how much. Okay, so notice we made a triangle here, right? Now we've got a triangle, and the blue dashed line, the part that we want, is opposite to the angle. So if you go back to trigonometry in geometry, if we're looking at the side that's opposite to the angle, then we need sine, okay? And so then your equation just becomes FR sine theta, and there you go. So theta should always be the angle between the force and the object, or the lever arm. Okay, and then just make sure you use the full force, right? Don't make things complicated. I've just seen this mistake, and so don't do that. If it says that if you push right here with 20 newtons of force, then use 20 in this F spot, okay? Use 20 right there, and sine theta will take care of the rest of it for you, okay? All right, mathematical similarities between torque and force. So the slide we just did is how to use force to calculate torque, okay? Because they're related. But there's also another way that this time this is not a direct relationship. It's just something that's really, really similar and helps to understand how torque works. So let's review just a second here. If we apply a force, it causes the object to accelerate, right? And we had an equation for that. It was Newton's second law, right? F equals ma, or sum of forces equals ma. So remember that sigma is just the sum of forces, or the total force. So this is the total force equals ma. Just wanted to remind you that this F is the total. Okay, so, but we also, 2 slides ago this time, talked about how if a torque is applied to an object, then the same thing happens. If you apply a torque, just like if you apply a force, because that's what there's a force that goes with that torque, then the same thing happens. It's going to accelerate, except it's just going to accelerate in a circle now. That's the only thing that's different. And there is an equation for this too. And here it is. The sum of torques, or the total torque, equals I alpha. Remember from last time that, so this is torques over here on the left with the tau. Remember from last time, alpha is acceleration, just circular acceleration or rotational acceleration. And I'll put those right here. Okay, but what I want to make you notice next is look at this equation and look at Newton's second law, and they're almost identical, right? Instead of force, we have torque. A is still A, it's still acceleration, just this one is normal acceleration, and the curvy alpha is circular acceleration. So acceleration is still there in both equations, and then force and torque line up really nice. So what is this I? What is this I? Because it does definitely match up with the N, and that's what with the M, and that's what we're going to talk about right now. This I is called moment of inertia. Moment of inertia, and that's like a really confusing phrase, I feel like, when I learned it the first time, moment of inertia, because when we think of moment, we think of time, But we should be familiar with the term inertia. We've talked about that before in forces. So let me remind you what inertia is. It's just a word for the fact that all objects resist a change in motion, right? So if you push on a car, it's going to resist you pushing on that car, right? It doesn't just fly away just because you pushed on it. It doesn't want to move. Newton's first law: an object that is still will stay still unless there's an external force applied. So it's sitting still, so it wants to stay still. It doesn't want to change. That's inertia. Okay, and mass is a measurement of inertia. Mass and inertia go together perfectly. More mass is more inertia, right? Because think about if you try and push on a small car, and then you try and push on a fully loaded semi-truck, which one's going to be harder to push? The semi-truck. Why is it harder to push? Because it's got more mass. And so because it has more mass, it's going to resist your push a lot more. So it makes sense that mass and inertia go together. Absolutely. The details about that though. So just like mass, inertia is how much is it going to resist moving? Something pushes on it. How much is it going to resist that push? Okay. There are formulas to calculate moment of inertia. It's on section 8.5 on page 210 in your textbook. And every shape has a different equation, so you're not going to be expected to, say, memorize those things. AP has even put out there that they're not going to expect you to know those equations. They will give you those equations, so that does mean that you need to know how to use them. Okay, so our example, as well as your homework problems, you'll have to calculate it, but it's just here's the formula, plug everything in, and it's all the variables make sense. M is mass, R is radius, and for like something that's circular, like a ball, R is radius, and so that makes sense from geometry. And if there's something like a rectangle or a rod, they use L for length, and so all the letters mean exactly what you might think they mean, and so the formulas are pretty decently easy to use. The one thing that you should know is that the moment of inertia does depend on mass. The more mass you have, the bigger I you're going to have. It depends on the geometry of the object, so what shape it is, and it also depends on the point of rotation. Kind of like how a couple slides ago we had those two spinning lines at the bottom, right? One spinning line had the dot at the center and spun around the middle. One line had the dot at the end and it spun around more like a clock. So where you're rotating also will change the I. Okay, so let's do an example problem here. A dad pushes tangentially on a small hand-driven merry-go-round and is unable to accelerate it from rest to a frequency of 15 RPM in 10 seconds. Assume the merry-go-round is a uniform disc of radius 2.5 meters and has a mass of 560 kilograms, and two children, each of those have a mass of 25 kilograms, sit opposite each other on the edge. So they're both on the edge on opposite sides. And we know the mass of each kid is 25 kilograms. The mass of the merry-go-round is 560 kilograms. The distance from the center to the outside is 2.5 meters. Okay. If you've never seen a merry-go-round, here's a picture of one right here. If you've never been on one of these, you are definitely missing out. These were absolutely the best playground equipment ever. Not a lot of playgrounds have them anymore, though, because unfortunately people manipulate them and use them in ways that are unsafe, and so they don't put them in a lot of playgrounds anymore. If you want to see what I mean, just go to YouTube and search merry-go-round fails. What I will tell you is that the merry-go-round itself does not fail. It stays very much in place and it spins exactly like it's supposed to. It's just people misusing playground equipment, but go check it out. You'll see. Anyway, so we know the size, we know the mass, and we know the mass of the kids. And this dad spins it. It's sitting still, and he spins it up to 15 RPM, and he does that in 10 seconds. Okay, so I'm going to go through one of these problems because the equation right here, sigma t, so total torque equals IA, is a simple enough equation, right? Oh, I gotta take I, and then I gotta take A or alpha, and I gotta multiply those, and I got my torque. Boom, done. Okay, but here's the thing: Your problems are not going to just give you a number for I and give you a number for A or alpha. There's a little bit of work for both of these things. And so I'm doing an example problem, and I'm going to point out all the spots where it's easy to make a mistake or not know what to do. And I'm gonna make big points out of each one of those. So what do we want to do? We want to calculate the torque, and then we want to produce. We want to find the torque that is needed to speed this thing up. We want to find the torque, and then eventually find the force needed to make that happen. Okay. So we need to find A, alpha, and we need to figure out I before we can do anything. Alpha, the circular acceleration, we're going to figure out just from its definition. From last time, the angular acceleration is just your change in speed, or angular speed, and then divide that by time. So how much did our speed change? Well, it started at 0. We went from 0 to 15. So how much did it change? It changed by 15. Now, the thing about that, though, is this is in RPMs, right? What is the M? This is revolutions per minute. And he did that in 10 seconds. So these units don't match up. This has got minutes. This has got seconds. So what we need to do is change that first. This is something that you want to be paying attention to in your problems as well. So we got 15 revolutions per minute, and we need to change that to seconds. So we divide by 60. And so we got 15 divided by 60 is 0.25 revolutions per second. It should get smaller, right? Because you can go around a lot more times if you have a minute compared to a second. Okay, so, and then we take that 0.25 revolutions per second, and now that we've got seconds and seconds to match up, now we just divide 0.25 revolutions per second, and then the time goes on the bottom. So there's 10 seconds. And what do we get? 0.025 revolutions per second squared. Now, the other thing that you need to know is that every time you do one of these problems, you need to have your acceleration in radians per second squared, not revolutions. It needs to be in radians, otherwise it doesn't work. So I said last time there is 2 ways to measure this stuff, but I'm going to go ahead and say that radians is needed for some equations, not all of them, but it is needed for some equations. And so since it is needed for some equations, that means we should just probably use radians all the time, because then we don't accidentally miss it when we need it. So what do we got to do to change that? We got to remember that 1 revolution is 2 pi radians. 1 time around, that's 2 pi. Just like in circumference, 2 pi r. 2 pi is 1 time around the circle. Okay, so we take 0.25 revolutions. Each revolution is 2 pi, so we multiply, and we get 0.157 radians per second squared. And that's what we got. So now we have our alpha. Alpha is 0.157 radians per second squared. So we had to use the definition right here, but we also had to change our minutes to seconds, and we also had to change revolutions to radians. Other than that, just divide by 10, and you're good. So these are things that you should be looking for in your problems. Making sure minutes and seconds, making sure all that stuff matches up, should be in seconds, and making sure that we're in radians. Okay, got to watch out for that stuff. Otherwise, this equation is super simple, right? That's not too bad. You take the speed and you divide by 10, but you gotta change some things around first to make sure it all works out. Okay, so we've got our alpha. Now we need our I. So I want to remind everybody about when we talked about systems, right? Open systems, closed systems. And we're not going to be focused on open or closed anymore, but we do need to be thinking about what pieces are there in our system, right? This isn't like pushing a box across the floor. There's multiple pieces. There's the merry-go-round, and there's the 2 children, right? So there's more than one piece. It's not like forces when we had boxes sliding down the thing. It's more complicated. A box is one thing. Now we've got multiple pieces to our setup here. You got the merry-go-round and the 2 children. So for our I, what we really need is a total I. So you got to do the I for child 1, the I for child 2, and I for the merry-go-round. Okay. Now, the one thing that is nice is that child 1 and child 2 should have the same I because they have the same mass and they're both sitting in the same spot on the edge. So that means that they're completely the same. So they're gonna have we only need to do I for one child and then just make sure to use it twice at the end. Okay. Um, so the moment of inertia, now remember that's what I is. Moment of inertia, that's what I is for the child. There's an equation for this. Like I said, you're not expected to memorize these. There's a chart of these equations in your textbook on page 210. This one actually is not there. I'll talk about that a little bit in the next slide. This is the only one that's missing though. But anyway, so this is the equation. This is a formula. All I'm saying is I'm telling you right now, these equations will be just given to you. You do not need to have these memorized. Okay, so I'm telling you this is the formula that we need for the child. And it's just mr squared. M is mass. The mass of the child is 25 kilograms. And r is how far are they from what the center of spinning. How far are they? They're at the edge, so that's 2.5 meters. And you got to square that. It's mr squared. So 25 times 2.5, and the 2.5 is squared. Put those together, you get 156.25 kilogram meters squared. All I do is put the units there together at the end, and then we got 156.25. Okay, and this is for both child 1 and for child 2. Okay, so we've got I for the children. We've got the moment of inertia for the children. Now we need the moment of inertia for the merry-go-round. Okay, so now the I for the merry-go-round, just abbreviated it right here. I, moment of inertia for the merry-go-round. The formula we need for that, because it's a cylinder, it's a very thin cylinder, right? If you think of like a soup can, that's a cylinder, and a merry-go-round is a cylinder. It's just a really, really wide and really, really, really flat one. The equation that we need for that is 1/2 mr squared. And so what's the m is the mass this time of the merry-go-round, which we know it's 560. And what's the radius of the merry-go-round? It's 2.5 meters. It's right there in the problem. So all I got to do is plug in. There should be a 1/2 here. Let me fix that. There should be a 1/2 here. Okay. And when you multiply all this together, put it in your calculator, you get 1,750 kilogram meters squared. Okay, so now we've got the moment of inertia for the children. We've got the moment of inertia for the merry-go-round. All we got to do is add those up. 156 for the first child, 156 for the second child, plus 1,750 for the merry-go-round. What does all that add up to? That all adds up to 2,062.5 kilogram meters squared. Okay, so we've got our alpha. We finally got our I. Now we just got to take these two numbers, plug them into the torque equation. Total torque is I alpha. Just take those two numbers, plug them in. All you gotta do is multiply them. Now that we have the I, now that we have the alpha, boom. Last step is super easy. Multiply them. 2,062.5 times 0.157 radians per second, our alpha from over here. What do you get when we multiply those? You get 323.7 Newton meters. And if you check your book, it's 320. They just rounded. I didn't round. I gave you the exact number. Okay, they asked for two things though. Calculate the torque, and also they want the force required at the edge. All we need to do, we got the torque now. We have the torque. This is the total torque, but there's only one force. So really this isn't a total. Well, it is the total, but there's only one. So there's nothing to add or subtract from it. This one torque is the total torque. Okay, so the only thing we need to do is use the first equation we talked about, which is tau equals Fr, torque equals force times distance. And we know the torque, it's 323. We know R because the dad is standing at the edge to push on the merry-go-round, so his R is also 2.5. We'll plug those in. 323.7 equals F times 2.5. We need F by itself. How do we do that? We just divide. 323.7 divided by 2.5. You get 129.5 newtons. There you go. All right. So it seems like a lot, okay? But the bottom line for the more complicated problems, this is one of the more complicated problems. Let me say that, is that the problems that come before this are a little bit easier. There's either also only one torque, or yeah, this is when it starts to get a little bit tough. 45 is very much like this one, except there's 4 rockets, and so if they want the force for just one rocket, when you get to the end, you're just gonna have to divide by 4. So there's 4 of them. That's the only I think that's the only difference. But let's kind of summarize what we did here. We knew we needed alpha, and that took a couple steps, making sure our units lined up and changing revolutions to radians by multiplying by 2 pi. But we got it. We needed to get our alpha, and we needed to get our I. And to get our I, we had to do I for each piece of our system, then add those up. So I for each piece, and then once you've got each piece, you just add them up. And then you're ready for the final step, where you just got to take your alpha, take your I, and multiply them. So once you have your alpha and you have your I, you're ready to go. Really easy. And then this equation is not too bad either, right? Once we had our torque, we knew the distance. The dad was where was the force? The force was from the dad was on the outside edge, so we had that radius too. And just a quick 323 divided by 2.5. Boom, there you go. All right, so it's not too bad. It takes a little bit of thinking about. If you're having trouble with these problems, I would really recommend like drawing a picture. A couple of the problems already have pictures in there, so that should help. But drawing a picture really helps with this kind of stuff. All right, a couple quick tips. In the last video, I talked about how to connect rotational measurements to linear measurements with velocity. So there was an equation in that video where V equals omega r. Your regular velocity is equal to your circular velocity. Just multiply that by r, the radius of your circular motion. And it's actually the same connection for distance and acceleration as well. So I can get regular acceleration by taking my alpha, my circular acceleration, times r, the distance of the radius of the circular motion. Go back and forth between these two pretty quickly. I can tell you for sure there is a problem where you will need actually this exact equation in your homework. A equals alpha r. You won't be getting little a. You'll have to get alpha. They give you it in meters per second squared. You need the circular version. There is, I did mention in that problem that there's one moment of inertia equation that's not in the table, but it is in the section, but you just have to kind of read. It's there and not too hard to find, but it's not in the table for you. And that's this equation that I used for the children and the problem I just did, mr squared. What this one is this is the moment of inertia for a point mass or a point object. So we didn't really think of the children as children. We kind of just imagine that they're little tiny dots. They're one single point with this mass at that distance. There's a problem where it's talking about throwing a ball with your hand and your arm. And so with the ball, you just pretend that ball is a single point. You're not really thinking about like when we did our system, for the problem example I just did, the system was a merry-go-round and each child, and it wasn't more complicated than that. We didn't think of the pieces of the child. They're just one little thing. So anytime you have like one little thing like that, you would be using this equation. If you're not talking about the big old shape, you're talking about one little thing, piece, it would be this equation right here that you need. Okay, so you will need this one as well. Definitely these two equations. The A equals alpha r and the I equals mr squared. You're going to need both of those in homework problems. Okay, that is the end of it here. Hope the homework goes well for you. Please, I've not been getting a lot of emails, so I hope that things are going all right. If you're stuck, send me an email. Don't sit there stuck. Send me an email. I'll do the best I can to help you out. And point you in the right direction. Okay. Don't hesitate. Just do it right away. On that though, make sure you're emailing my .org account and Christopher@plano88.org. Make sure that's the one you're emailing, and I'll get it and I'll help you out. Okay. continue pushing through, everybody. It won't be forever, so that's the good news, right? It ain't the best, but we're doing it. So keep up the good work and take care for now. See you next time.